sort of thing. These filters are very, very thin, and even just one tiny particle, too small to see, could penetrate them during launch when it's being shaken around. So we had to keep everything scrupulously clean, which means doing everything that has to do with the inside of the detector assembly in a clean room.
A clean tent works by pulling the air in at the top and passing it through special filters to remove dust particles. This raises the air pressure inside, which keeps outside air from coming in. Keeping the clean tent environment virtually dust-free requires the use of special clothing commonly referred to as bunny suits. It also requires cleaning all items entering the tent and the use of special materials.
This is clean room paper, but when you run it through the printer, you get a lot of toner on it, so you have to wipe it off before you take it in the clean room. Wow. Tedious, but it does come up pretty black, so it's... Yeah, why am I wiping paper off? Well.
Meanwhile, just across the center, another team is building the 5 X-ray telescopes.
X-ray telescope development is a lot like any other instrument developed for spaceflight. We make small components like reflectors and we test them. We make assemblies including many reflectors and we test that assembly. We make the full-up telescope assembly from those and we test it, and we test, and we test. Because you have to know it's going to work on the ground, because you can't fix it in space. We're making the 5 telescopes for the XIS instrument and the XRS instrument that'll be on board the Astro-E spacecraft.
The telescope mirror manufacturing process begins with raw materials like the metal foil.
The earliest operation is foil cutting and forming. We have to produce upwards of 10,000 foils for the one mission in order to get the 6,800 foils that we need to fill up 5 telescopes.
The technician puts the foils through a special roller.
This is going to impart the gross curvature that we need and the slight bit of conical shape that we want. And then you'll put that stack inside this little window here. This forming mandrel has a cone shape that is the proper prescription for its place in the mirror. While it's still under vacuum and so the atmospheric pressure is pressing them against the mandrel, it takes on the exact shape of that mandrel.
The X-rays that Astro-E2 will observe get absorbed in many materials, including glass and ordinary mirrors. So Astro-E2 and other X-ray telescopes require a unique strategy to focus X-rays onto a detector.
We use an X-ray telescope which depends on a grazing incidence reflection in which the reflectors are nearly edge-on to the X-ray source. The X-ray beam hits the primary reflector, then hits the secondary reflector, and then moves on to the detector about 4.5 meters away. We add a pre-collimator before the primary reflection to block off-axis X-rays. So now they have the proper figure, is what we say. They're curved just right, and they're smooth enough on that surface, but they're still not shiny enough. Then they go down to the replication lab. They've been busy cleaning up the glass mandrels, and then they're put into a gold deposition system, and gold is deposited on that outer surface of that glass tube mandrel. You spray thinned out epoxy on the foil. And once it's in vacuum, that round mandrel is lowered and it just sits on top of the foil.
Maintain my time.
So then we put that mandrel inside an oven and bake it overnight. And it's not a real bake, it's just 40 degrees C. gold won't stick to glass very well. Through a process that is more magic than anything else, we lift the foil off of the mandrel, and the gold that had been on the mandrel now is stuck to that thin film of epoxy, but the front surface of this foil sandwich with gold on the front has the surface quality of the glass mandrel.
Back at the CRIF, the XRS team detects the first sign of problems.
So this is really what we're seeing. This is really the indication of trouble, of a leak, which is that when we close off the valve, the leak rate goes down. We open the valve, the leak rate goes up.
Sensors detect a small helium leak inside the dewar.
And we did another check over here as well. So this step here, from this low level, which is almost zero, up to here, is our leak. That's the real solid indication.
We had a very small leak, and it was so small that it was almost impossible to see at room temperature. It was only when you made the system very cold that the leak would get big enough that you could see the helium coming out.
That has a couple of implications. First of all, obviously, is right now we have an extremely tight schedule, delivery schedule, so this now potentially jeopardizes the delivery schedule. All of the instruments that we build for use in space are one-of-a-kind, very unique instruments, and so we allocate some time in our schedule to deal with problems and unexpected things. In this particular case, we're dealing with something that's really difficult. We have a very, very small leak that we can only detect when the instrument is cold, and therefore it's going to take a lot of effort and a really heroic effort on the part of the team to try to find this problem, fix it, and get the instrument back together and into Japan when we said we would.
As the XRS team races the clock to solve the helium leak, the X-ray telescope manufacturing process enters another phase, testing.
We've now gotten foils that have the front surface we want, and it goes into the metrology lab where the foil is inspected.
A WICO profilometer measures using light, so it's a non-contact method. It uses visible light to actually measure the roughness of the surface. As far as X-rays go, these are pretty close to mountains. But these are very short mountains, being only about 1/1000th height of a human hair. So we would like to have them just basically as small a difference between the maximum and minimum as practical.
So then they're graded, some are rejected, some are what we call flight, and then some are put in a small class of usable if you have to get yourself out of a jam.
All the parts are ready.
So we're going to start building up a telescope, and we do this one quadrant at a time. After you put the bars in, you put one foil in the middle of the housing somewhere, and you put it on an alignment fixture. The alignment bars are the ones that create the angle and perfectly position the foils in the housing. Make it so that we can stick one housing on top of another and have 175 concentric nestings line up perfectly with 175 below.
After spending days in an exhausting effort to fix the helium leak and stay on schedule, the XRS team now faces an even more serious problem.
There was a leak which turned out to be in the vent line, and we found that with this leak detector, and were able to patch it and repair it. And unfortunately, what happened was during the testing of the repair, we got an ice plug in the helium fill and vent lines for the test dewar, and that actually ruptured and caused some damage. This, of course, has set us back quite a bit.
The XRS team goes into crunch mode, with shifts working around the clock to fix the damage, test the system, and get back on schedule. It's become the most grueling, the most trying few weeks the XRS team has had to go through. Tension strains the team, testing nerves and